So all are between this. Let us draw it 1 second afresh. We'll draw it like this. This is how you get all these three line current. C dash. This is your VA is equal to VL equal to V phase because it is a delta connected load. Okay. And what we are measuring, if you look back here, we are measuring between the line voltage VA and VC. So VAC, and we are measuring current through current coil IA dash. So to find out, to measure the voltage VAC, we should get, this is your VA and this is your VC. So VAC means equal to VA minus VC, right? So if you take VC in this side, and if you complete the phasor sum, this is your theta, this is VAC. And another one, when you are measuring IBB dash, you are measuring the voltage between VBC. So VB minus VC, VB minus VC. So minus VC is there, is here. So if you complete again the vector sum, it will be somewhere here. So this is your VBC. This is VAC. So this angle is equal to 30 degree. This angle is equal to 30 degree. This is theta. So wattmeter 1 will measure what? It will measure √3 into VL, because VA equal to VC equal to VL as I have shown before. And when you take the phasor sum of these two within angle, it is 60 degrees. So you will get √3 VL, right? VAC. That into your IA is equal to IL, because this is your line current. Then cos of 30 degree minus theta. So it depends. If theta equal to I mean, if it is very lagging, then of course, if it is theta is less greater than 40, so we should take theta minus 30, or if it is less than 30, then it will be somewhere here. So 30 minus theta. So difference between these two. And then W2 is equal to √3 into VL into IL. This remains the same. Now this angle, total angle between BB dash and BC is 30 plus theta. So cos 30 plus theta. So now if you add them up, W1 plus W2, you get √3 VL IL, and here this is going to be 2 into uh, cos 30 degree into cos theta. Or yes, this is cos 30 and this. So cos 30 equal to what it is? No, there I made somewhere some mistake. Let me just go through it. This is your field. This is I phase, no? So I made mistake here. This should be IL. IL means your I phase here for this particular delta connection. IL to be equal to I phase into root 3, isn't it? Because IL plus this I phase equal to I phase. So IAB minus IAC is equal to your IL. So that will be root 3 into this. So here what you are measuring, this is actually IL, and what you are obtaining here, this one, it is root 3 into VL, because this is VL and this is also VL. So between AC and AC, so V AC should be equal to this only, root 3 only. So
There is a direct relation.
this should be not there. This root 3
Sir,
won't be
my
there.
doubt is there.
Yes.
Sir, IL is equals to root 3 I phase. Sir, but
Hmm.
in the previous vector diagram, we
Hmm.
have seen that in the delta connected load,
Hmm.
the IL actually lags the I phase by 30 degree. So, sir, is that included in the relation, or do we have to again multiply the magnitude and reduce it by minus 30 degree?
Not very clear. Tell me, repeat once again.
Yes, sir. Sir,
Hmm.
sir, when we derive the relationship between IL and I phase of the delta connected load,
Hmm.
sir, there the angle was coming between IL and I phase as 30 degree, and the magnitude was root 3 times that
Huh.
of
Yes,
this.
yes,
So,
yes,
sir, that
yes.
is included the angle, or we have to again include the angle while actually writing the equations.
Whenever you are measuring your, when you have a say when you are using a wattmeter, and then your pressure coil is measuring that which voltage that phasor and which current that phasor, difference between them you should take. Okay, so if I revise it, your I think I should revise it for two different connection, then it will be clear to you. Let us first do it for the yesterday's class. What I did for star connection or delta connection. Can you remember it?
Sir, I
So
think star connection we did.
okay. We'll redo once for star connected load. Star connected load. Okay, and then we'll redo for the delta connected load. Let us do it for the first for the star connected load. So I am not drawing off the alternator side. I'll just connect this load terminal, which is your phase A. This is B. This is C. So this is your this is your IB, IA, and IC. So IA equal to IB equal to IC, that is equal to line current, and that is equal to phase current for here, right? Agree? This is one relation. And if you have the phase voltage, which is VA here, and then VA is equal to VL by root 3, isn't it? Where VL is line to line voltage. Okay, so whenever we connect a wattmeter here, and the same way there, this is your 2 wattmeter connection for the start connection. This is W1, this is W2. Okay, so what is your voltage across this? It is between A and C, right? This is your terminal A, this is your terminal C. Within these two terminal, your pressure coil of the wattmeter is connected. So that's why if we just draw the phasor diagram here, this is your phase voltage VA, this is your phase voltage VC, this is VB, and phase current is equal to let us take it in a uh, less value. Means your angle is of lower value. Okay, so this is your phase current IA, IB. because your wattmeter current coil is measuring your line current only, and your line current is equal to phase current. So this is theta, this is theta, this is theta. Then now this measurement of voltage is VAC. So between A and VC. So we take minus VC this side, and we complete this phasor sum of this minus VC, and then this is equal to your VAC. So now what is the angle between VAC and IA? This is this much, na? So it is 30 minus theta. And for the other one, VB and VC, if you complete here, this is going to be your VBC, and this is 30. So it is total is 30 plus theta. So W1 is VAC into IA into cos of 30 minus theta. What is VAC? VAC equal to line voltage. That means VL. What is your IA? That is equal to IL. What is cos theta? Minus that will leave like this. And W2 is equal to VBC into IB into cos 30 plus theta, right? So you again substitute VL, IL, and here it is cos 30 plus theta. So if you add them up, W1 plus W2, it will come out to be VL into IL into 2 into cos 30 into cos theta. So it is root 3 into VL, IL, cos theta. Okay, and if you take W1 minus W2, you will get this is equal to 2 into sine theta into sine 30 into VL IL. So you get VL IL sine theta. So if you multiply both sides with root 3, then you will get total reactive power. So root 3 into W1 minus W2 will give you your Q, which is reactive power, and this is your P. So if you now take P square and Q square, you will get the instantaneous power. Okay, and tan theta equal to root 3 W1 by minus W2 divided by W1 plus W2. Okay, so this is for star connected load, and let us now do it for the delta connected thing. So when we go for the delta connected load, these are all same, which are equal to Z angle theta. A, B, C. So here your wattmeter W1 and this is your W2. Pressure coil is connected between A and C. So what is VAC? VAC equal to your VL, right? This is delta connected load. So VL is equal to V phase. Now come, what is your current? Current is equal to, for the wattmeter 1, it is IA. So IA is equal to what? It will come out to be root 3 into I phase, isn't it? If it is a balanced load, right? So now these are the two relation which we need to keep in our mind. Now we'll just draw the if we draw the phase voltage here, if these are the phase voltage, I mean your VAB, AC and BC, these are the phase voltage, and that is same as the line voltage. Now what is your phase current? Your phase current, this is your VAB, VBC, VCA. Okay, so now when you check your wattmeter W1, there it is measuring VAC between these two. VAC, that means this one. So you can, if you just really want to take polarity, then we'll take in the other side. We'll see how we'll draw it. Now your phase voltage, and on top of that you will have your phase current. So what is your phase current? For this, for this is your VAB, right? So here this is your IAB, and this is your IBC, and this is your ICA. Same theta. Now you have to measure this IA, right? This IA you want to measure by wattmeter 1. So what is your IA? IA is equal to IAB. This is your phase current, IAB minus ICA, right? So IAB minus ICA. If you take ICA this side, this is theta. This is ICA, I minus ICA. So if you take the phasor sum of these two, this is your IA, right? And this angle is equal to 30 degree. So what you are measuring using this wattmeter, you are measuring IA, which is equal to your IL, and you are measuring VAC, this is your VL, and the angle between these two is equal to um, uh, 30 plus theta. So cos of 30 plus theta, right? So wattmeter reading W1 is equal to VL into IL into cos of 30 plus theta. Okay. Now we should take up the other one where we are measuring the voltage VBC, and what is your current you are measuring? This is BC and this is your IB. So IB current is equal to IB plus phasor sum of IB plus IAB. If you write KCL here, is equal to your IBC, isn't it? In this way. So your IBC minus IAB. So this, if you take the phasor sum of these two, this is minus IAB. This is your IB, right? This is 30 degree. And you want to measure the angle between, you want to measure IB and IBC and IB, isn't it? Here, so what is the angle between, uh, this is your 30, this is theta. Okay, so what is going to be the difference between these two? Between, I think I made some mistake regarding polarity. Your polarity here, you are measuring between AC, na? There I put, did I take AC properly? This is AC. AC means it is here. Okay, okay. This one is mistake. So this is 30. I have taken here cos 30 plus theta. This angle should not be right because we are measuring for W1, which is AC. So AC is in the other side. So somewhere here. So if this is VAC, then what is the angle between 60 degree and what is this angle? It is 60 degree minus 30 plus theta. This 2 is 30 plus theta. This is 60. So it will be actually 30 minus theta, isn't it? Because this is your VAC and this is your A. Okay. And for this one, you will get, for W2, you will get VBC into IB into cos 30 degree plus theta, this angle, because this is your VBC and this is your IB, and here this is VAC and this is your angle. So it is 60 minus, actually this is equal to 60 degree minus 30 plus theta. Okay, so it is actually 30 minus theta. So if you solve it, you will arrive in the, at the same equation like before. if you solve it. So this is for delta connection. This is delta load and this is star connected load. Oh, what I have done, it got perturbed actually. So I hope in recording you'll be able to find it out, and in any book you will get it. I'm sorry because I messed up this. Somehow it has gone, huh? It's like this. Okay. So this is how we can get the total power consumption with two wattmeter method. And now you check if we just want to plot the ratio between W1 and W2 and the PF. When your PF will be 0, when your PF will be 1, when W1 is equal to W2. So this is 1, this is also 1. When your PF will be minus 1, or sorry, when your PF will be 0, when W1 is equal to minus W2, because PF is what? We have active power consumption VL cos phi is equal to W1 plus W2, and root VL sin phi is equal to root 3 into W1 minus W2. So tan phi is equal to root 3 into W1 minus W2 by W1 plus W2. So when your cos 90 is equal to 0, so then tan 90 will be equal to infinite. So W1 is equal to equal and opposite sign. So then it will be PF will be equal to 0. So when it is minus 1, this will be 0. So if you plot like this, it is a plot like this. If you check the plot with respect to the ratio of W1 by W2 and PF, then at some point you will get the value which is your half. So when it will be half, when this is tan 60 equal to root 3, then it equal to half. So when W1 is equal to W2, that means W1 minus W2 is equal to this is 45. I mean, when you put 10 6 5 equal to 60, then it will become what? It is root 3. So you get W1 plus W2 is equal to W1 minus W2, right? So uh, what will be the value of that? W1 minus W2 equal to 1. So W1 minus W2 is equal to W1 plus W2. So you get one wattmeter reading to be equal to W2 equal to 0. So W2 when it becomes 0, then you get your power factor to be half. So it is like this. Depending on the ratio, you will get your power factor. So whenever you get, actually theoretically you can get W1 and W2 is negative, but actually when you practically want to measure it, you will not get this, because whenever your power factor is going beyond 90-degree, it will always become negative. So at 90-degree it will be 0, and then it will be negative in that way. So when you do that, when this situation arises, then you will see that in one wattmeter you are not getting deflection, it is trying to deflect in the other way, so it will get somewhere settled below 0. Okay, so in that case you understand that there should be negative reading, so you have to change polarity of one current or one voltage of your load, and then only you will be able to find out your proper measurement. And then when you get the measurement in wattmeter, but while noting or while calculating, you should put minus sign because you have changed the polarity. So whenever the angle between some voltage and current, line current and some line voltage is more than 90, then if you just change the polarity of voltage, then it will be less than 90. Like if it is 120, then if you change the polarity, then it will be 60 degree only. Or if it is 110, then it is 70 degree. So in that way you'll be able to find out the wattmeter reading, which you can measure using meter, and then you should put the sign as negative. Okay, so now let us gradually move to 1 wattmeter method, which is used to uh, volt, find out the reactive power for any balanced three-phase load. Okay, so let us again draw star connected. Same thing you can do for the delta connected load. Where this is VA, VB, VC. This is the current coil of the wattmeter. This is the pressure coil of the wattmeter. So only wattmeter W you are using, and your current coil is connected in series with this terminal. So you are actually measuring your IA, and your pressure coil you have connected between this is C. So between B and C. So you are measuring VBC and you are measuring current IA. So then what you will find using this wattmeter, let us see. So we'll complete this. This is star connected. So your phase current is equal to line current. Phase voltage is root 3 time of. For phase voltage and line voltage, you should do the phasor diagram. So VBC, this is VA, phase voltage, VB, VC. But if you want to find out your VBC, which this wattmeter W is measuring, then you should take C in the other side, complete the phasor sum like before. This is your VBC. And what you are measuring? You are measuring line current, which is equal to IA. And a line current is equal to phase current. So this is theta, this is your IA. So now what is this angle? This is 30 degree, right? Once you do the phasor sum when it is balanced, so this is 30 degree. So then what is the difference between IA and VBC? So your wattmeter reading W will be equal to VBC into IA into cos of, this is 120 minus 30 minus theta. Am I correct? And VBC is equal to your V mm, phase into root 3, or you can write directly as VL. This IA is equal to IL, and this is cos 90 minus theta. So isn't it? This is phase. So if it is V, this is VL, this is sine theta. So then what actually you are measuring? If you just multiply W into root 3, then you will get root 3 VL IL sine theta, isn't it? And what does it means? This is equal to Q. So this also equal to Q. I mean, wattmeter reading will be in watt only, but you will get the value which is your reactive power. So this is the 1 wattmeter method to find reactive power. Okay. So this is all about your wattmeter connection for power consumption, to measure the power consumption, active power consumption, reactive power consumption. So you can, if you have 2 wattmeter, with that you can measure all active and reactive power for a balanced three-phase system. I mind you the term balanced. For unbalanced, you have to use 3 wattmeter only. There is no other way. Okay. 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 Let us now take one problem. So the problem says about a balanced. We have a balanced delta connected load which is three phase of 30 kilowatt, power factor 0.7 pf, which is fed from 400 volt 50 hertz supply. Okay. Now it is, you can see that if your power factor is 0.7, it is okay, but in some cases power factor even can go bad for the highly inductive load. Then what to do to improve the system system stability and retain the power measurable power? You the supply for the supply you should use the capacitor bank to improve it. So that is called power factor improvement. And to improve that, so to improve the power factor, improve the power PA from 7 to 0.85, uh, we need to use a capacitor bank, delta connected capacitor bank. Okay, find out the capacitance. Find out each capacitance, means its balance also, the capacitor bank. So this is how it will look like. This is your, say, alternator or source, whatever it is. Maybe capacitor, maybe your transformer also. And this is connected to your load, which is 30 kilowatt, PF equal to zero 0.7. And then to improve the power factor, you are adding a capacitor bank like this. So this is delta connected. You can very well understand that. So this C you need to calculate. This is delta connected. So how can we do that? First, what is given? It is given your you have a delta connected load. So this is also delta. You can draw in terms of delta also. No issue. And it is a RL kind of load, as you can see. Power factor improvement using capacitor bank means, of course, it is a RL kind of load, so it is lagging. And then we can find out the current first, because we are given the power factor, total power consumption, and the supply voltage, right? So what is your supply voltage here? Supply voltage is equal, we can write first P equal to root 3 VL IL cos phi. So what is your VL? This is equal to 400 volt. So P equal to what? It is 30 kilowatt. So 30 into 10 cube is equal to root 3 into 400 into what is your IL. IL we need to calculate. What is your cos phi? That is equal to zero point 0.7. So you can calculate IL, which is line current, and that comes out to be 61.86 ampere. Okay. So it is a delta connected load, delta connected load. So I phase is equal to IL by root 3, and that comes out to be 35.72 ampere. Okay, so this is your current, and this is current drawn by the load, and now you have to improve the power factor. So how can you do that? For that we need to draw per phase circuit. So you can see that this is also delta connected, and if I just redraw it, if I redraw this, this will look like, it is like same. So we can draw a resistance, inductance here, resistance, inductance there, between these two line, between here and inductance here, and there also resistance and inductance, and these are all same.
Sir, the two delta connected system are in
Hmm.
parallel.
Yes, in parallel, because this is one triangle, this is another delta. Okay, these are in parallel. So if you take par phase kind of circuit, then this will be your par phase thing, right? So your line current is 400, so 400 fold by root 3, then that you have one capacitance in parallel, and then one resistance and inductance are in parallel. So this C, this is your load. So you know the current for it, right? What is your current? Phase current you have already calculated. You know, you don't know the angle. So you don't know means you have not calculated the angle, which is, if you want to write in form of angle, this is IL, this will be 35.72 angle cos inverse zero point 0.7, and that should be minus, right? Because this is a lagging, right? So you can now draw your phasor diagram. This is your IL, and this is your I phase, rather will write, and this is your IC, and this is your I, or like that only. I mean, this is how you are improving it. So now if I draw the phasor diagram, this is your voltage. Sorry, this should not be 400 by root 3, it's my mistake, it should be 400 only. No, here this is your voltage, which is line to line voltage, and across it we have one capacitor and one RL. Same for other part, there is also one capacitor, one RL. Same for this, between this and this, there is also RL and capacitor. So this is 400 volt, and this is all about. Okay, so now what we can
Sir,
uh,
one thing,
hmm,
sir, 400 volts specified in the question is the phase voltage of the power supply, no?
it is not phase voltage, it is line to line voltage, is fed from a 400 volt supply. You have a delta connected load which are connecting to 400 volt supply. So this is what actually, this side you are not given, na? You are given only this, and it is not mentioned, but if unless it is not mentioned as phase voltage, you should take line to line voltage or line voltage, which is 400. Okay,
Okay, sir.
because even though it is star connected, here line to line will be 400 only, na? And we are not taking this as our phase. This is different, that is different. So from here onwards we are taking this as your line voltage, because we don't know what is there in the alternator side, whether it is star connected or delta connected. We know only about our load. So we take this voltage to be 400, and then per phase we have this capacitor and this resistor and inductor. Okay, and we can draw the phasor diagram like this. This is your 400 volt supply. As it is a parallel circuit, so we'll take 400 volt as our phasor, And then initially when this C was not present, then we had this, right? This is your I phase. And what is that angle? This angle is equal to, uh, sorry, cos inverse 0.7. And now you want to use a capacitor in parallel. So this is your IC, which will be 90-degree leading your 400. So you have now IC plus I phase. So if you do this phasor sum, so this is now your new I, and that is the new PF. If this is theta 1, this is theta 1, theta 1 is cos inverse 7. Now this is your theta 2. So what is your theta 2? Theta 2 is cos inverse 0.85. This is what we are doing. This is your source, and this is your initial lagging current, and then once you add a capacitance in parallel, this current will be like this. So this is how your power factor will improve from theta 1 to theta 2 as the angle is reduced from theta 1 to theta 2, because theta 2 is less than theta 1. Okay, is it clear?
Yes, sir.
Okay, fine. So once it is clear, then we can find out what is your I current we require. We know what our phase current, right? I phase is equal to 35.72. So we can write this I, we need to find out this IC. If we can find out IC, then IC is what? It is 400 by capacitance, 400 by the capacitive reactance XC, that is equal to your IC. So we need to find out our IC. So I phase cos theta 1 is equal to your I cos theta 2. So this is one relation, isn't it? Your I phase is 32.35.72. Cos theta 1 you can find out from here, and cos theta 2 you can find out because theta 2 is also given. So we can write this as I is equal to, this I is equal to, I phase is 35.72 into cos theta 1 is equal to zero point 0.7 divided by 0.85. Am I clear? This is equal to 0.85 given, this is equal to zero point 0.7 given. I phase we have calculated here. So from here we can calculate I, which is turned out to be 29.42 ampere. So we got, this is our I. And then once you know this, then you can find out your IC, which is equal to I phase sine theta 1 minus I sine theta 2. Is it okay? Because this is basically your I phase sine theta 1 and this is I sine theta 2. So difference between two is your IC. Or you can, if you just resolve it, I phase sine theta 1, this is I phase sine theta 2. So if you subtract this, then you will be able to find out your IC, just like the vector diagram, as per the vector diagram. So if we do that, then this is going to be your uh, phase is 35.72. It is sine of cos inverse zero point 0.7 minus this is 29.42 sine of cos inverse 0.85. So if you solve this, this will come out to be 10 ampere. So once you get IC, then what is our IC? IC is also equal to your V divided by XC. So your XC is what? It is V equal to V equal to 400 volt, as you can see from phasor diagram, and this is equal to 10. So you get XC to be equal to 40 ohm. So 40 ohm is basically equal to omega C. So what is your C? It is 1 by omega by 40. And what is your omega? It is 314. Why? It is 2 into pi into 50 hertz. So is turned out to be 79.61 microfarad. Okay, so this is how you should create your capacitors bank so that you can get your power factor improved from zero point 0.7 to 0.85. Okay. So in the next class, I'll show one example which is of unbalanced load, that is on Monday, and then we'll gradually shift to transformer, single phase transformer, and with that our course will be concluded. Okay. Okay. Thank you.
Thank you, sir.
Thank you.